We're going to continue talking about NP-complete stuff. No review today, just 2 reductions. We're going to do a reduction from 3 satisfiability to vertex cover. And then we're going to do a reduction from vertex cover to Hamiltonian circuit. And these 2 reductions are going to kind of fill up that picture that we did last time, filling in the connection of the tree, showing that all these different problems are NP-complete. This takes logic stuff and connects it to graph stuff. And this takes graph covering problems and connects it to a different kind of graph problem where you're looking for a path. They're both relatively difficult reductions in the sense that the problems look very different from one another at first glance, and you have to work hard to make the connection. The good side of it is that once I show it to you, it isn't too horrible to figure out that it works or why it works, but it is a little hard to imagine how you thought of it in the first place. Okay, here's my examples. This reduction needs to go from a formula, a Boolean formula, and convert it to a graph with some number. And the Boolean formula is supposed to be satisfiable or true if and only if that graph can be covered with that number that we give it. So we got to come up with a graph and a number. The graph's got to have that vertex cover number if and only if this formula is true. How are we going to make a connection between those 2 things? In order to do it, we have to take our formula and convert it to a very special kind of graph that we have some control over the vertex cover of that graph. Where the hard part of whether the vertex cover actually can be done in what the time in the number of nodes we expect, where the hard part is encoded into the Boolean formula satisfiability part. So all that's a lot of blabbing. Let me give you an example. Here's the reduction with one example.
Vertex cover, right? Is that the vertex cover problem?
Vertex cover is the one where you want to take the smallest number of nodes and cover up all the edges on the graph. So here's an example. I'm going to do an example where it is satisfiable and one where it isn't. So you can see how the graph has the vertex cover and then how it doesn't have the vertex cover. So here's a very small example of the 3-sat problem. It's definitely satisfiable. Right? You can pick x true and y true. It's kind of easy to see that it's satisfiable. So whatever graph we'll come up with here that's going to be equivalent to this, the answer to the vertex cover question will be yes on this example, because the answer to the formula here is yes. Let me show you what we come up with. It's very similar to another reduction that I asked Mark to do in recitation that reduces not all equal 3-sat to the simple max cut problem. It's very similar to that. So you've seen something like it before. Here's what we're going to do. For every single variable in this formula, I'm going to construct a piece of the graph. And for every single clause, I'm going to construct a piece of the graph. Here's how it works. Look at your variables. Count how many there are. There's 3 of them, x, y, and z. You're going to have one node for each x, and one for x bar, and one node for y, and one node for y bar, and one node for z, and one node for z bar. And you're going to connect them with edges. So it looks like this. I'll label them so we can remember what they stand for. That's the first part of the reduction. The second part of the reduction is to take every single clause and make a triangle for it. This is the beginning. This is the structure. These represent the edges. These represent the variables. These represent the clauses. We're encoding this problem in a vertex cover problem. How's there going to be a connection? Each of these triangles represents one of these clauses. So we're going to take every node, 1, 2, and 3, and connect it to the variables that make up the clause, namely x, y bar, and z bar. So it looks like this. X, y bar, z bar. And the same with the other one, x bar, y, and z. X bar, y, and z. That's the graph that we construct from this formula. And you'll see why in just a second. Right now it just seems like magic. but there's a very good reason why we do this. I haven't yet told you the vertex cover number that we're trying to get. So let's try to figure out what that should be. And this will be our graph. And then we'll put the k up here. That's the vertex cover that we're trying to get. We'll calculate what that should be. Look at this graph for a minute, even before I put the middle edges in. When I just had the edges up here and the triangles. How many vertices do I need in a vertex cover for that graph? I got these edges up here. Each one of these edges needs 1. That's equivalent to the number of variables I have. So I definitely need n for the number of variables, in this case 3. I got to have one of each of these pairs of nodes in there to cover the edge in between them.
But is it guaranteed that a given z and z, a given a and a bar are both in the clauses? I mean, why can't a sit around as a singleton without any?
It could. It doesn't have to have anything connected to it, but we still have to cover this edge here in between the two. So one of them has to be in there.
You would introduce it even if one didn't find it among the
Yes,
clauses.
yes, yes. It would be in the graph regardless of whether anything connected to it or not. Yeah.
Need one for each clause. Two.
1 or 2. We certainly need at least 1. Do you need 2 also? You got a triangle. You got to get all 3 edges covered. Can we cover all 3 with just 1 node?
That we
No.
get the top covering them too.
Well, forget about the middle ones.
We need to.
But even if you had the top covering it, if you only had one of these nodes covered, it would cover this edge and this edge, but it would leave that one out, regardless of how many you had up on top here. So we're going to need at least 2 for every clause to cover the triangles. And that means, let's say the number of clauses is what do you want to call it? M. Fine. So it's n plus 2 times m. That's what we're going to need. We need at least that much. The question is, can we do it with that much? Do we need more? Or can we do it with just that many? If you can answer the question whether this has a vertex cover of this many nodes, that will correspond to the same answer of whether this formula can be made true or whether it has to be false. And I'm going to convince you of that right now. Okay, let me stop for a second. Who's with me? The construction of the graph and the construction of k is the reduction. Now we need an argument. Now I need to convince you that this graph can have a vertex cover of that size k if and only if this is satisfiable. Greg?
Can you tell me what k and n and m are again?
N is the number of variables. And m is the number of clauses in the formula. So in this graph, what's the vertex cover we're looking for in this graph?
Four, seven,
Yeah.
1, 2, 3, 5, 7. In this example, we're looking for a vertex cover of 7. We're trying to see if we can do it. If we can get a vertex cover of 7, I'm going to convince you that that means there's a true-false assignment in this formula that makes it true. If we need more than 7, then I'm going to convince you that there's no way to have a true-false assignment here, that it has to be false. Okay so far? So let me start to convince you of this. I need to show you there's a relationship between whether this formula is true and whether this has a vertex cover of size 7. We have 2 directions to go here. I have to show you that if there's a true-false assignment, then there's a vertex cover of size 7. If there's a vertex cover of size 7, then there's a true or false assignment. So we can pick either direction to go first, and let's pick this direction. Let's say there's a true-false assignment. How do I get a vertex cover of size 7? I'm going to tell you exactly how. I'm going to make a one-to-one connection between these 2 solutions. Give me a true-false assignment, and I'll explain it to you, and then I'll do it in general. So what's a good true-false assignment for this formula? X is true, Y false, Z true. That's fine. So here's what I'm going to do. I'm going to look at all these variables, true, false, true, and I'm going to mark the ones that are true and cover them.
Actually,
It would also work if we only had x is true and z is true, and that would be a more restricted situation for your connection. So could you do it with just the two?
Well, you could. It's more flexible for me if I don't get to choose this. So,
That gives you less paths to convert.
well, you can pick this any way you like. You can pick this false or true. Is that what you're saying?
Well, what you just said is that you're going to start and color those paths that are designated by these formulas. And if you only have two paths to cover, if you only have x is true and z is true.
You want z to be false, you're saying?
No, just get rid of y. Don't designate anything about it. So just x is true and z is true. Then you've only got two paths to cover.
Well, then I'll say that I can make y anything I want it to be. If you're not going to tell me, then I get to choose the vertex cover myself. I'm just showing you that I can come up with a vertex cover of size 7 if you can come up with a true-false assignment. If you think this is already an assignment, then I get to pick anything I want for y. Okay. So I don't think it's going to make it harder for me that it's f. But if in the middle you want to change it to t, we can make it t also. You'll see. So let's cover the x, because that's true. Let's cover the z, because that's true. And the y is false, so which one is true? The y bar is true. So let's cover this. This true-false assignment tells me which one of each pair to put in the vertex cover. Well, you know we have to put one in there anyway, at least. So this tells me which ones. That's fine. Now, how do I continue finishing up my vertex cover? We know that we have to put at least 2 in every triangle. The thing is, we also have to cover these edges in between. So let's look at the first one. The first one connects to an x, to a y bar, and to a z bar. How many trues are in this clause? There's 2. See how this edge is covered because it connects to a true one? And how this edge is covered because it connects to a true one? So I don't have to cover either of the other ends of those 2 if I don't want to. I have complete flexibility. All I have to make sure I cover is, which one? This one here has to get covered so that that edge gets taken care of. And I can pick either of these any way I want. I got a lot of flexibility. What about this last one? I got to cover this one because it's not covered. This is like the false variable. So I put x's on all the spots that connect to false variables. This goes to a true, this goes to a false. Here I got no choice. I got to cover this one and this one. But I'm okay. I managed to do it in 7. How come? What let me do this in 7? The fact that every one of the triangles is connected to at least one variable up on top that is true. And I mark those in the vertex cover. So since I got 3 edges to take care of that go in between, from here to here, and at least one connects to something that's already covered, I can use my other 2 to cover the ones that go to empty spots. So this definitely covers the whole graph. It covers the bottom because I have 2 in each triangle. It covers the top because I have 1 of each pair. And it covers all the things in between because I specifically chose to cover the 2 down here that connected to empty nodes, that connected to edges that weren't yet covered. And the third one was the one that was true, that already connected to one that was already marked. And I could do this no matter what true-false assignment you gave me. I go through marking these true, and then go to every clause and mark the 2 that might connect to falses. And I always can get it done with 1 of each of these pairs and 2 of each of these triangles. So if there's an assignment, true-false, then there's a vertex cover of size 7. All right, so many, many curly looks on faces. Let me stop for a second. I'm not going to go on if you have questions about this. This is really all there is to say about this direction. We have to go back in the other direction now to show that if there's a vertex cover of size 7, then there's also an assignment, because it might not be back and forth. We have to show it both ways. But before we do it, let me stop for questions. Everybody has this. It seems a little magical. I think I kind of get it, but I still don't get it. So how can I help? Questions?
Is this covering every case? Is it just this amount of nodes, or?
Well, this could be as long as you want,
Okay.
and I just have a bigger graph.
Okay. With the same number of variables.
No, I could have as many variables as you want. This takes any formula and makes it into a graph. I'm going to do another example in a minute that has 4 variables in it.
So as long as you have a triangle in the bottom for each pair, it can be as long as it wants to be.
And the triangle doesn't have anything to do with the number of pairs. It has to do with the number of variables.
The triangle, I have as many triangles, Chris, as I have clauses. I got a triangle. This one represents x, y bar, z bar. And that one represents x bar, y, z.
If there were 4 variables, they'd be rectangles? Is that
No. 4 variables would just have 4 edges up here and as many triangles down here as there were clauses. But this is 3 sets, so there's no... Right. And in fact, but Brian's got a point. This reduction would be a lot harder if I didn't have 3 set. Part of which makes this easy is that I can use triangles here. And that's why we have 3 set. It's to make reductions like this easier. So I don't have to worry about that point. Otherwise, it would be a bit tricky to take care of that. What's up, Chris? What?
just getting closer to the board? But you have x and x bar, y and y bar, z and z bar, right?
Yes.
Those are pairs of negated variables. Right?
Yes.
So
Well, they're edges in my graph, but they represent pairs of these variables. Yeah.
So it seems to me more of a function of the number of pairs of variables than of the number of rows in your normal file.
What's more of a function? The size of the vertex cover I'm trying to get?
No, the picture that you draw, isn't it just a...
I have as many edges as I have variables, and I have exactly as many triangles as I have clauses.
Okay.
So if I have 8 clauses, I'm going to have 8 triangles in the bottom with lots of edges coming up to the variables to connect them. Not sure yet? Almost? Should I do another example and then we'll...
It has to be 3 set. I was trying to figure out the constraint between the number of variables and the number of rows. Because couldn't you end up with not enough?
Couldn't we end up with not enough what?
No, you can't because it's 2 set. Okay, I get it.
Well, let's do an example where there's no formula, and I'll show you that there's no way to get the appropriate vertex cover. When there is a formula, I've tried to convince you that there's always a way to get the appropriate vertex cover. We have just enough slack to handle each of these triangles with 2 and to handle all the edges in between. Because the 2 vertices we have can be used to cover possibly the ones that go to empty edges. This one and this one. These 2. And we don't have to worry about covering this one because this edge was covered by the true variable. As long as every triangle has at least one true variable, then one or more of its edges in between here is covered by that variable node. So we can use the other 2 to cover the other 2 edges. All right. Let's do an example where it doesn't work out. And I'll show you that it's both ways. Yes, the answer here is yes to here. No, the answer here is no to here. So let's,
The fact that they're arranged as pairs,
yeah.
is that just coincidence? If those were 6 different variables,
You mean the fact that I label them XX bar?
and they're grouped like that,
You mean that they're not connected to one another? It's important that they're not connected to one another, but this notion that they're paired like this just means that a way for me to explain to you how if you give me a true-false assignment, I'm going to cover particular variables here and find the cover in a particular way. This edge is going to correspond to the first variable. If you say true, I'm going to have the left one covered. If you say false, I'll have the right one covered. And as long as every clause points to something that's marked true, that means every clause has at least one edge that goes up to something that's marked. That edge doesn't need to be covered in the triangle. So I can use my other 2 to cover the other edges in the
you
triangle.
could have up to 6 variables in one of these things with 2 rows, right? I mean, if they were just a plus b plus c and then d plus e plus f.
Yeah.
Here, so then you'd have 6 sets.
Oh, you could. You can have an arbitrary number of edges on the top and an arbitrary number of triangles on the bottom.
But in that case, you'd still only have 2 triangles on the bottom, right?
Yes. You'd still have 2 triangles on the bottom and 6 edges on the top.
It doesn't seem like, I mean, the reason this works out is because you have a triangle for each You have one fewer triangles, and you have pairs up on top.
Okay, so let me do an example where I have 3 variables and 4 triangles. Well, that won't work. You didn't expect that to work.
Right.
Whether the number of variables in the clauses does not say whether 3 sets satisfiable or not. It's just coincidence that when there's fewer clauses, it's going to be doable, and when there's more clauses in the example I give you, it won't be. It's possible to come up with examples where that's not true.
So the relationship of the number of sets.
It's just coincidental. Yeah. Let's look at this example. X bar y v, X bar y v bar, y bar x v, y bar x v bar. Here are 4 different clauses, and we're going to try to make the graph for this. If you stare at these clauses for a while, you realize there's no way to make all these 4 true. No matter what you give to x, y, and v, there's always one clause that stays with all 3 of its variables equal to false.
But
And, yeah?
y bar is in 3 of them,
Yeah, it's okay.
so make that false and make x or v.
Oh, sorry. Now it's right.
You actually said y and wrote y bar.
Oh, I said y and wrote y bar? Yeah. This is right. Let me just double check it now that I made a claim that isn't. Now what I said is really true.
But it seems X bar, Y bar true given a solution, right?
Yeah, x bar and y bar would work.
No, I don't think so. If x bar is true and y is true,
So now you've got x bar in the top 2 and y bar in the bottom 2.
If X is
So
true,
if x
If
and
X
y
is
are
true-
both false, then
if
all
X is
4 are
true
true.
and Y is true,
if x is true,
No, x is false.
If x is false,
x
then
is
y
false and y is.
Or
Or
either way.
Yeah, either way.
This has a solution? I wanted one that
Yeah.
doesn't have a solution.
It would also work.
Hold on.
If x and y are both true.
X and y are both true and this is fine?
Yeah.
Ugh. Well, that means whatever graph I come up with would have the right vertex cover, huh? I wanted to get one that wasn't true. I thought this was one, but now let me think.
Can you work backwards?
Yeah, and there's a lot of ways to come up with ones that aren't satisfiable.
You start with the chart, make a chart that doesn't work, and then generate the...
If you could do that, then you'd understand this reduction completely, so that'd be a good exercise. I'd rather come up just with a formula that we know definitely doesn't work and then show you why the vertex one doesn't work. But now I'm... What if I made these like that?
Just make 3.
Well,
No,
no,
then
only one
X.
of them, and then change only one of them, and then change the x bar up there. One of those. And that
What about that?
Yeah, that might do it. Maybe.
If you have each variable having 3.
I think this is okay. This doesn't have any way to do it, right?
Y true, X true,
Y true, X
Now you
true,
have x true and v false.
and V false, yeah. I'm trying to make it obviously wrong. I'm trying to do the obvious. Yeah.
If you have one of each variable and then the other 3 are all negatives, then you can't have. Then one of the clauses has to be false.
Okay, so
You do it with
Just-
two,
just-
just
just
say
do-
X, Y,
have
V,
one X and
and then
3
not,
X bars.
X bar, Y bar, V bar.
but I need to have 3 things in each clause.
That's what I just said.
Yeah.
X, Y, V, and then next clause is X bar, Y bar, V bar.
No.
That's not enough because I can make the X true and the Y true. Right.
And that. Y false.
Just make them all bars except leaving one of each variable not.
I could do all 8 possibilities. That's true. Is that what you mean, Blake?
I don't think so.
What should the next one be then?
There doesn't need to be another clause.
Oh. What should I do?
Put in the third line. The third one should be X bar. Maybe make the
So
top
all
one
3 set instances are satisfiable. That's what we decided now. Make the top one what?
Y bar and V bar maybe.
Now, if you've got x bar X bar is in 3 of them. It can't be in 3. Because then you just said X bar, and then in the other one you said any of the others.
All right, let me stop for a second. This is actually, although I don't necessarily have an example that we know is satisfiable or not, this is actually a really good exercise, because here's the thing. Say we don't even know the answer. Don't try to figure out the answer. You don't know if this is true or false, right? I'm going to convert it to a vertex cover problem. Maybe some of you are better at that. Okay, and you can tell me whether it's got the right vertex cover, and I'll convince you that that will answer this question about satisfiability. Fair enough? All right, let's make the picture and then analyze the vertex cover of this picture. What you're going to find out is that all your thinking about whether this is true or false is going to be the same kind of thinking that goes on as to whether this picture will have a vertex cover or not. And that'll really convince you of the reduction, that the thought processes are identical. So let's go ahead and make this work. How many variables do I have here? I'm going to need more room. I'll do it here. I got x, y, and u, or v, right? X, y, v. And how many clauses do I have? I have 4 clauses.
Yeah.
4 triangles. Okay, and now I have to connect them according to the way it says here. X, y bar, v bar.
Aren't we supposed to connect them according to whatever we... Oh, never mind. Sorry.
X, y bar, v bar, right?
Yep.
X, y bar, v bar. The most important thing is that during this reduction, I have no idea whether this is true or false. I have to do this blind. I have to just go ahead and create this graph. And I'm doing it. X bar, y, v bar. X bar, y, v bar. The third one is y bar, x bar, v. Y bar, x bar, v. And the last one is y bar, x bar, v bar. There it is. And the number we're trying to get is 1, 2, 3, 5, 7, 9, 11. We're trying to get a vertex cover of size 11. Let's try to get a vertex cover of size 11. Everybody knows we got to pick one of these from each of the edges, because we got to cover this edge. So which do you want to do? Pick them. Let's try. All right, let's do this one because that has a lot of edges. That seems like a good idea. Let's cover this. Let's cover y bar, and let's cover v bar. That was intuitive, right? Because they connect to lots of edges. That's fine. Now let's go down to the clauses and see if we can handle them. This one connects to an empty spot. This one has to get covered. Otherwise, nothing's ever going to cover this edge. What about these two? Well, we're going to... They're both covered already, so we could pick one arbitrarily. Doesn't matter. Handle that one. That was easy. What's that equivalent to? That's the same as noticing that if we set x to false, y to false, and v to false, that both y bar and v bar are true. That means both of these edges are covered. That means we only have to handle a single false variable. So what we just succeeded in the vertex cover problem is a success also in making this first clause true. Now let's go to the next one. This guy's already covered, so I'll just x the other two. This guy's already covered, so I'll x the other two. And this guy's already covered, so I'll x the other two. It was kind of easy to get a vertex cover of size 11 here, right? That means there's got to be a true-false assignment to this thing. And what is it? It's x bar true, y bar true, and v bar true. That means x, y, v are all false. And that will make this work out. So we hesitated in this example, not noticing whether it was true or false. We converted it to a vertex cover problem. We handed it to somebody who does vertex cover problems quickly. That was Gary. He noticed that the biggest edges should be covered first because it was more intuitive looking at it as a graph. We finished it. It worked out fast. We converted it back and we noticed, okay, for sure there's an assignment here. There's a vertex cover here of size 11. There's definitely an assignment here, true, false. Now that's the same example I gave you last time in the sense that there was a true, false here. Now there's a vertex cover of size 11 here. But this time I kind of argued in the opposite direction. I said, come up with a vertex cover and I'll show you the assignment. I'd still like to do one example where there's no way to get a satisfiable assignment and we actually have to use more than 11. So I'm going to try to do that right now. But before I do, are there questions? Yeah, Kevin.
Maybe this is a question for later, but I'm just kind of in the vertex cover problem as it's sort of presented to us. There's no constraint over which nodes we choose.
None at all.
Cover.
None at all.
So I could imagine a situation in which, if you have the constraint of like you have to choose either x or x bar, y or y bar, v or v bar, you can't get the number of nodes and in the right number of time. But I could imagine, a false sort of Boolean statement where you have a whole lot of these triangles connecting to one of these things that would be false, where you might be able to get the vertex cover if you were to choose both x and x bar. And so I'm wondering if I'm wrong that there's no way to do that, or
you're saying it would be false,
right?
But you'd be able to get a vertex cover by choosing two of these.
Yes.
If you chose two of these, you'd have a vertex cover of at least 12 or more.
Okay.
Right? So the answer to this, you would fail. Because we're trying to get 11. It's never any help to pick an extra one. Because that automatically kicks you off the S chart.
Is that...
Because
I see what you're saying.
The question here is, can we do it with 11? And I've set this graph up specifically.
You'll always need 2 on the triangles
regardless.
Okay.
Right. You don't get any help on the cross edges by making, on the triangles by making 2 of these. Right. But
it's important to, that's an important part of the proof, right?
It's a big important part of the proof that every triangle needs its own 2, regardless of what goes on in the top. Because you have these edges here.
But it's also, it's just...
And it's an important part of the proof that I nailed down this graph. I nailed down a specific graph that I could say something about the vertex cover of this graph. And because I nailed it down in such a specific way, I got to make the relationship to the formula.
I guess I'm just making the point that if you're just from the perspective of a reduction, if it's a vertex cover problem, but you're saying that, okay, we have to choose either x or x bar, you have to also sort of explicitly show that if that constraint weren't there, that the vertex cover still wouldn't work.
What I have to show is that if you have a vertex cover here, it corresponds to a true-false assignment here.
Right.
Obviously, if I pick 2, it wouldn't correspond to a true-false assignment here. So my convincing you that that's true is that you can never get 11 unless you have exactly 1 here.
Sure.
And at that point, I'll say just use whatever one is here to be the true. So it's an if and only if. Yes, absolutely, it's an important point. Yeah, Mike and then Joe.
Okay. If you have x, y, and v true,
Yeah.
that was your initial guess, then it wouldn't work because that fourth statement's false. So then you have to be good at guessing, basically, which ones.
All I'm saying is that if there is a solution here, then there's one here. If you pick a bad solution here, it would correspond to a bad one here.
So when we find one that doesn't work, we basically have to test all the...
No, because we're not doing this as an algorithm. I'm just showing you that if there is a solution here, then there's going to be one here. I'm not saying...
You might not get it on the first try, is what I'm saying.
You're never going to get it at all. That's the whole point. It's hard to get this one, so it's going to be hard to get this one. We're not going to try to get it. If you try to get it, the best you could do is try all of them.
So if you try like x true, y true, and v true,
Yeah.
it won't work on this. You can't
Right.
get it in 11. So when we do one that doesn't work at all, and our initial guess says, oh, it doesn't work, we have to go through and say, hey, maybe another one will. Yeah.
Yes, and I would convince you that none of them will. Maybe I should do one example like that, where it doesn't work. I tried that, but I know when it'll work.
This doesn't reduce the computational complexity any by making this.
Right. It doesn't make it easier. It just shows that it's just as hard as this.
Okay.
Finding an answer to this is just as hard as finding an answer to this and vice versa, actually.
And they're both exponential.
They're both real hard to do. They're both real hard to do. Yeah, Joe?
If you add the clause X, Y, Z on the other side, could you just show what happens with the triangle over here?
Yeah. I got a new triangle. It connects to,
This can't be true, right?
I don't know, connects to X, Y, and V. And right now, all right, so let's look at Joe's example. It's a very nice question. Let's say I had this extra clause, and this was here. Then this particular choice of vertex cover doesn't work anymore. Why not? Because I have a triangle down here. It's connected to three things that are not marked, an X, a Y, and a V. That means these three edges aren't covered. That means the only way for me to cover all the edges in this graph is to do what now?
Have a different.
Either try a different thing on top or color all these three, right? Or color a duplicate up there. But that makes me have 12 or more. Now, if every single thing I try here is going to be like this, where one of the triangles ends up going back to 3 empties, then I'm dead and I'm going to have to use 12. So if there's no way to do this, there's going to be no way to do this. Now, I don't know that there's no way to do this one yet. It's just that this particular one I tried didn't work.
So you would try another one.
We'll try a different one. I don't even know if this has a vertex cover or it's satisfiable.
Switch V. Yeah, switch V.
Just switch V the other way? All right, so that takes care of this. That means I can make both of these X's and be safe. And does anything else?
It changes.
I have to move this one to here to handle that edge. Anything else? Was this one helpful somewhere else? It was helpful here,
But you could choose either, so.
but that didn't matter. Is everything else okay? Are there any empty edges? Any 2 empties in between? No. No. So that's okay.
So now solution is X bar, Y bar, V.
Right, right. The key thing is that a solution to this is a solution to this and vice versa. They are completely intertwined. You can find me a vertex cover of size 11. You solve my satisfiability problem. You solve my satisfiability problem, then I got a solution to this vertex cover of size 11. Yeah, Chris?
Really peculiar graph. That's not actually a practical reduction of that to this, right? It's like it's a very practical reduction of this to that. Like this proves the vertex cover is NP-complete.
Right.
But if we had proven that vertex cover was NP-complete, this wouldn't be a proof that 3 satisfiability.
Not at all. That's exactly right. Right. This, if you didn't know anything about 3 satisfiability, and you had known that the vertex cover was NP-complete in advance by some other method, then doing this reduction tells you nothing. Okay? This is only a useful reduction because we went from an NP-complete problem to an unknown problem, and now that unknown problem is at least as hard as our NP-complete problem. A solution to the vertex cover problem now implies a solution to this. Okay? But a solution to the satisfiability problem does not let us do vertex cover problems in general. It lets us do vertex cover problems that look like this. If you gave me a general graph that doesn't look like this, off the bat, I don't have the slightest clue how to turn it into a formula. In fact, there must be a way, because every problem in NP can be converted to satisfiability. So there is a way, but we haven't discussed it. And you're 100% right. This does not imply that vertex cover reduces to 3 satisfiability. The dual directionality here is in the proof that the solution to this is true if and only the solution to this is true. But the reduction is in one direction. It's a very good point you made. It's an excellent point. Other questions? This is an example of what I think is a hard reduction. Kind of you have to see the big picture of how vertex cover ends up doing Boolean formula. And we're going to do one more, and then I will let you rest from these hard reductions. Then we'll talk about that game. Vertex cover reduces to Hamiltonian circuit. Here's my problem. Here's a graph. Does it have a vertex cover of size 2? What's the answer, yes or no? It does. Okay, these two are fine. Does it have a vertex cover of size 1? No. Answer to this is no. Answer to this is yes. I'm going to describe a reduction that takes this graph and a number and converts it to another graph. The new graph is going to have a Hamiltonian circuit exactly when the answer to this question is yes, and the new graph will not have a Hamiltonian circuit when the answer to this question of vertex cover is no. The two reductions that I'll do will be the same graph. One will use k equals 2 and one will use k equals 1. So you can see an example of a graph that has the Hamiltonian circuit and one that doesn't have the Hamiltonian circuit. And this is the same kind of component style that we need something in the circuit to represent choosing vertices that we're covering here. This is a very difficult reduction to come up with, but not so bad to understand once you see it. Same as the example before. All right, I want to give you the big picture of this reduction first and fill in the details as we go so you don't lose the idea. I want to give you some sense of how somebody who comes up with these reductions is thinking, instead of just making it seem magical like the last example. The way to really do these is you see a few magical ones, you try some on your own, you imitate the magic, and then you check it. And you see, oh, it doesn't work, I don't really get it. And then one day, you kind of get lucky and it works. And then you say, oh, maybe I get it. And then after a while, you start to look the big picture, and you start to plan in advance. You start to see the idea. The idea is you want to somehow mimic, in a Hamiltonian circuit problem, the idea of covering vertices. Here's how we're going to do it. The first thing we're going to mimic is this 2. Okay? We're going to have 2 nodes here. That corresponds to this 2. If k were 1, we'd have 1 node. The Hamiltonian circuit is going to run from here down to some components over here, fill them all up, come back to this one, fill the rest of them all up, and come back to here to end. Everyone understand the general picture? If there's a way to cover this graph with 2 nodes, then whatever graph I come up with here is going to start at this point, cover some components that I'm going to create, go back to here when it's done, cover the rest, go back to here. Did I do that right? Go back, right. Cover this, go back to here, cover the rest, go back to there. You can't go back to the same one. I meant it right, I said it wrong. Start from here, cover some components, go back to this one, cover some other components, go back to here, complete the cycle. All right. Every time we move from this node, go through some things, and go back to the other node, go from this node, go through some things, and go back to the other node, that will correspond to covering a vertex in this graph. For example, if I cover this vertex, which edges actually got taken care of? These 3, right? I'm going to have some components down here that represent edges. When I leave this node, I'm either going to be able to cover these 3 edges if I chose this one, these 2 edges if I chose this one, these 3 edges if I chose that one, or these 2 edges. I'm going to have those 4 choices. If I choose these 3 edges, I'll go through all these nodes down here, finish it up, come back here. There's going to be edges left. If I can get the rest of them, I'll be okay. This is still going to seem like the clouds until we do some more details. But we are going to need to represent edges somehow. And we're going to need to represent the fact that all these 3 edges come to a point here. All right, let me stop for a second. I didn't say too many details yet, so there's not much you could ask. But nevertheless, there are questions so far. I'm going to need a component for every edge. How many edges do I have in this graph? I got 5. Now these components are going to be a little bit hairy looking. So instead of actually drawing them, I'm going to kind of make a schematic for them and then tell you what's in them later when we have to decide exactly how they have to behave later. So for now, let's say they look like this. They're little robot men. That's one edge. I'm going to label these now. A, B, C, D. This will be the edge AB. There's actually a whole bunch of stuff in the middle that I'm going to do later. I'm going to show you what every edge looks like later. If I make the big picture now of the edge, it's going to just... Every edge looks like this with something in the middle. I'll show you how they're connected later. And I'll tell you why. But for now, just let's write all the edges down, because it's going to look like a mess if we do too much at once. I need 5 more edges. What else do I need? I got AB. I need BC. I need AC. I need BD and CD. What's left? Just CD and then I'm done? Okay.
What does the robot guy stand for?
Each one of these edges is a robot guy. So I create the robot guy. I haven't shown you what these robot guys really look like. There's more nodes and stuff inside. If you want to know, each one of these, instead of being 4, is really going to be 12 nodes big with edges between them. There's going to be a lot more in there. But it's all for details. It's all for a particular purpose that you'll find out in a minute. But I want you to get the motivation for why we put these weird things in the middle. I'm not going to put them in the middle now before you know why we have to do it. For right now, we're in the dark. We came up with an idea of trying to make a Hamiltonian circuit run through here, through some of these components, back to here, through some of the rest of the components, back to there. Somehow it's going to correspond to covering up nodes, and somehow each of these edges has to get covered. So covering an edge means going through it on the path. Okay so far? All right. The one thing I haven't done, which is kind of crucial, is that if I decide to cover B, then AB, BC, and BD all get covered. So I need to connect these edges up in such a way that when I decide to go through a path that represents covering up B, that it actually goes through all these edges, all 3 of them. So I need to look at those 3 edges. Where are they? AB, I'll check them, AB, BC, and what's the other one? BD. I need to connect these up. And I'm going to connect them up in a very simple way. I'm going to just decide to consider the 3 of them as a group. And I'm going to connect, it's these 3, right? So I'll connect this guy to here, this guy to here. And now they're a group.
Is that arbitrary as well?
Completely arbitrary. I'm saying you 3 join hands.
The way that you connected them was arbitrary. You could have
You
connected.
take any of their points and connect them to any of the other points on the other robot guys.
You could have connected B prime to B prime instead of B prime to A.
That's kind of important. Yeah, kind of arbitrary.
Kind of in the eye.
Is what's inside these things the same for every one of those squares, or it's going to be different?
They're all going to be the same. They're all going to be the same. What's inside all the squares is all going to be the same. I'm hesitating because you guys asked me how I'm going to connect these 3 together, whether it's arbitrary. And I said it doesn't matter which one you connect to which. And then you asked me whether you connect the B's to the A's or the B's to the B's. And now I'm hesitating because I want to make sure nothing goes wrong. Yeah, I think I don't like this. This I don't like. It's arbitrary as long as you do it right. I'm connecting these guys together by the same letters, not by switching different letters. So I connect the B prime to the B and the B prime here to the B, and now I've got these 2 ends.
So that would be true for every
So if you
should connect to somewhere.
if you wanted to connect A.
So we just connected, let's see what we just did. We just made a connection that if we decide, say we're over here and we're covering vertices. If we decide to cover the vertex B, that gets us through this edge, continues us through this edge, continues us through this edge. That means if you cover the vertex B, you're really covering a component that does AB, BC, and BD. It's a way of connecting these three edges into one group that relate through the B.
So when you enter B, you exit B prime?
Exactly. When you enter B, you exit B prime. You enter this B, you exit B prime. You enter this B, you exit B prime. And then when you're all done, where do you go? Back to here.
So B prime goes back.
So both of these connect to B, and both of this connect to B prime. That gives me the choice of, from either one of these, starting here, and when I come back, I can come back to either one. All that represents these three. This is hard. I still need to represent this, this, and this.
It doesn't seem like such an arbitrary choice anymore.
Well, it's arbitrary which one of these three you would these endpoints are arbitrary.
Okay.
I have a whole bunch of things that align, and the two people on the ends that connect to the choosers, that's arbitrary. Okay. Let's keep going. Let's do this edge, this degree. I have to connect the edges CD and BD.
So you're going to be going in the D and
So
the D.
where is that? CD and BD. It's these two. I'm going to be going into, it's the D that we're doing now, right? So I'm going to go into this D, come out here, connect up there, and connect these two to here, and these two to here. Even this example seems to be a little too big to do.
Couldn't it be smaller though?
I often just do a triangle, but then it's... Should I just do a triangle?
No, this is fine.
No, keep going.
Keep going? All right, let's do this edge now. I got to do AC, BC, and DC. AC, BC, and DC. I'm coming in through C. I come in through C. I come out through C prime. I come in here. I go out through C prime. I come in here. I go out through C prime. Back. Back. And there's another one.
Is that the original end?
There we go. All right. Only one more. AC and AB. This focusing on going into A. AC and AB are here. Oh, they're right next to each other. Good. So I go in here. I come out here. I go up here. I come out here. That's it.
Well, it's obviously a circuit.
There's a circuit in this graph if there's a vertex cover of size 2 here. There's no circuit in this graph if there's no vertex cover of size 2. All right. You all know there's a vertex cover of size 2 in this graph. You all know that the vertex cover needs to be, it's got to be B and C. I'm going to show you what path corresponds to choosing B and C. Everybody ready? I start here and B. I choose my vertex cover. I'm going to show you what circuit corresponds to it. Start. It was a voice from heaven yelled, different color.
We can do this even still not knowing what's inside the little boxes.
Yes. You're going to come up with a question while I do it, and that's what motivate what's in the boxes.
I'm counting on you, Mike.
I'm counting on you. We're choosing B and C. Start from here. Go to a B. I only got one choice. Now, do not go back up to this one. Instead, I get to choose. I'm showing you the circuit. So don't tell me I have to go the wrong way. I'm telling you the right way to go. Go through this whole component and look at B. Look at the edge here. What edge is this one that we're going through right now? BC is covered on both sides. Do you see that? It's covered on both sides. That means we're going to end up later on going through the C side. So I'm only going to cover the left side here. And I'm going to come out. I'm going to leave this side uncovered. Okay? Now I'm going to continue over to here. And that's the edge AB. And that's only covered one time. So what I'm going to do here is I'm going to cover everything and come out. I made it all the way through. Now let's continue. I go back here. Wait. There should be another one. Oh no, thank goodness. There should be one more. Good. Now I'm going through this edge, BD. BD is covered only on one side. This is our last chance to cover this edge. So cover it all up. When you're covering an edge from two ends, the first time you come through it, you cover the left side. The second time you're going to go through it, you'll cover the other side. But when you're covering it completely only on one side, you take it all through. So that means here we go through everything and come out. And now we go all the way back to vertex cover number 2. Vertex cover number 2 is going to be C. That means we're going to go to something that starts with a C. There should only be one possibility here. Goes over here to the right. This is the second one, so I'm making it jaggedy.
Or different color.
How about purple? Okay. Notice, now we're back. You see we're coming back to the same edge, hitting it for the second time because we covered it twice. It's okay to cover an edge twice. Sometimes you do it. Now I take care of everything in the component, but only on the right side. And I continue on to the next part, which is the edge AC. I have to take all of this in, finish it all up, come out, take all of this in, finish it all up, come out, and boom, there's my circuit. Everything in here got touched once, exactly once. I started from that spot, went back to here, continued through, and ended back up where I started. It's hard, it's complicated. This is one direction. And in this direction, we actually don't need anything special about the robots except the ability to do what? We got to be able to just go through the ones on the right, or if we need to, go through all of them before we go out. That's all we need. So here is a possible way to do that. What if I just made the robot look like this? Those were the four things, the B, C, and the B prime. Is that good enough? I could come in here, go out that way, or I could just go down the side. It looks like that's good enough for the robot. So let's make this our first approximation on a robot. Just a simple square. Everything works okay so far. But I'm not done with the whole argument. To finish this argument, I have to show you that if there is not a vertex cover here, then there's no Hamiltonian path here. Or equivalently, if there is a Hamiltonian circuit here, then there's going to be a vertex cover of size 2 here.
Figure for something that has more than 2 connections.
What do you mean something that has more than 2 connections?
Or actually, maybe that one. Here we've got up to 3 edges coming into to a vertex, what if we had 5 or 6? Is that going to affect it?
No, it doesn't affect it at all. You just connect more robots together.
Okay.
The reason this isn't good enough is because if there were a Hamiltonian path here, I need to come up with a vertex cover. How am I going to come up with a vertex cover? Only if my Hamiltonian path satisfies a particular restricted thing. Remember I said my Hamiltonian path goes down here and I want to say where it goes, so I go this way? What if it comes in here? What if I have a Hamiltonian path that comes through here? I want to show you it's a vertex. I want to come up with a vertex cover for it. But say it goes around this way and comes out this side. Suddenly my whole sense of connecting the Hamiltonian circuit to a vertex cover goes out the window. I wanted to make sure that when it goes in B, it has to go out B prime, so that it has to continue on all the other edges that are connected to that B. That would imply some kind of a vertex cover. But if I can go in here B and sneak out here on the C prime side, I might be able to get this whole thing done with a Hamiltonian circuit, even though it wouldn't correspond to a vertex cover at all. I need to force, when I go in on B, I need to force it to come out this side. Otherwise, I don't have the reverse argument. So this first approximation to a robot is not good enough. It's good enough to let me get all the possibilities. That's important. It's good enough to let me go on the left side. That's important. But it's not good enough because it doesn't force me to come out this side all the time. I could choose to come out the other side in a Hamiltonian circuit, and that might not correspond to a vertex cover.
When would B prime ever be connected two other ways so that you would be passing through it at some point in the future?
Well, it's connected to all these other ones, so maybe I could come back in through A prime, sneak back through this B and this B prime, and come back the opposite way.
But those would have...
I guess you could go from BC, but you couldn't. I don't think you could do BC and C cover BC, C prime being inappropriate.
So Chris is wondering, maybe this still does work, and we have to make some argument that it still might work?
Well,
maybe.
That particular thing, I don't think it works, because there's only one edge coming into B prime from some other robot.
But there might be a lot of things going to B. B might be part of... There's a lot of edges that end in B. There could be a CB, and an EB, and an FB. And they're all going to have little change that run through this.
B prime specifically only connects to another B.
This one only connects to another B. Right. So the issue is whether we could somehow get this later by coming back through here and zigzagging our way out through the other side.
You couldn't in this particular
In this particular case, we can't. But it's going to be hard to argue in general. All right, well, let me do this. Let me make you a picture of what the actual one looks like. Here's what a robot really looks like. Here's what an edge really looks like. Say you come in this side. If I come in this side, convince me that when I end up coming out the bottom, I can't come out on this side. You have to really think about this. This was constructed just for this purpose. It was constructed just so that if you came in on this side, you're never going to get a Hamiltonian circuit if you end up coming out on this side. Let's try. How could we come out on this side? We could go down this way. We could come up here and down through there. If you do that, then these guys are stranded. If you come up this way and this way and this way and come up down here, then this guy is stranded. If you try to come in one side and come out the other side, you strand a vertex on the side that you came in on, which can never be gotten. The only way you can get through here and leave a possibility for a Hamiltonian circuit is there's two possibilities. One is this way. Just come straight out. That corresponds to us taking the left side. What's another way? That's the only other way. That's how you get both sides when you're picking through a vertex. So this was constructed, this silly little component is constructed just specifically that when you enter it, you have to leave the same side if you have any chance of getting a Hamiltonian circuit, but you have two choices. You can either choose that this vertex covers only one side of the edge, like the BC edge, or you can choose to get the whole thing like you do for the AB and the BD edges. And you can see that picture. This corresponds to going through the whole thing. This corresponds to going only through one of them. Donna, what?
So when you come in the C side, aren't you eventually going to come in there and just shoot down?
If you came in the B side and did all of this, then you would never come in the C side again. That's the equivalent of like an AB edge. If you came in the AB edge, Donna, like here, here's the AB edge, you came in the B side, you take this edge, you come out, and you're never ever going to cover this edge again because you never go in through A. But when you come in a BC edge, where we're actually going to go to it twice, the first time we come in, do the left side, the second time we come in and do the right side. This is very common in NP-complete problems in these hard reductions, that you design something that gives you just enough flexibility, but not too much. It's like a good straitjacket, good magic trick straitjacket. You want to have just enough room to be able to model the left side or the right side or both, but not enough room that you can go through this any darn way you please. You want to be able to constrict the Hamiltonian path enough so that any one of them will correspond to a vertex cover. All right. What if k was 1? Then you take one of these vertices and throw it away with all the things it connects to. Then I claim you're never going to get a Hamiltonian path here. You can try to go through B and try to get everything as you go through, because you're never going to have another chance to get back to this side. If you have one vertex on top, you get to go down, you better go through everything, and then come back up. You got no other chance. So let's say you're going to try to cover it. You only have one. This one's gone. You start here. You come down, you go through B. You cover everything on your way to make sure that you don't lose anything. You come out, you cover everything on the way. You come out, you cover everything on the way, and now what's your choice? Only to go back. You leave out the edge AC and CD. That means you covered B, and you left out the edge AC and CD. Exactly the edges you've left out. Your path left out those chunks. The pieces of the path that are left out correspond to the edges that were left out in the vertex cover. So you can only get a Hamiltonian circuit if there was a vertex cover with this many nodes covering it, if and only if. This is hard. This is the hardest reduction we've done. This is in some sense as hard as reductions get, in the sense that if you really can grab this one, you're at a very high level. But I think now we'll just stop for questions. You need to think about it a little more. I might be able to go over it more informally in the afternoon if we have some recitation or something, but I think we'll let this example go right now. Are there questions about it? Yeah, Teresa.
Why is it 12 nodes rather than just four on the top and 4 on the bottom? Why do you have those intermediates?
If we just had these,
Well, and then another 4 down below. You've got ones in between them. Why do you have like 6
You've
on
got
the
6
side
on each
rather
side.
than 4 on each side?
Yeah, maintain the crossovers.
like what if I just do this?
Yeah. No,
No,
well, you
that's-
have them separate.
With a space
You have
between them.
Space between them.
Oh, okay. I understand your question. Like this.
Yeah. What are those? Yeah.
What do you lose?
Because then you
by
can,
losing
because
those?
then you can go out C. Because then you can go out C.
I can come in here, come this way. Oh, no, I can't. It's okay, but I can do this. That won't hurt.
You go down the first, then up, then down, then
Here,
down to the left,
I can do this.
down to the right.
Yeah, sorry, I didn't make the right picture, but it's going to be trouble. Here, we can do this. I come in here, I go up here, I come down here, down here, down here, up here, and No.
Go.
Ugh. Hold on, Teresa. Let me redraw this and answer your question. All right, so before I answer your question, let me remind everybody what has to be true. This component needs to satisfy certain principles. One principle is that if you go on one side, you have to come out the other side, and on any piece of a Hamiltonian path. And the other principle is that you have the ability to get this half or get all of them. So first of all, let's make sure we have the ability just to get this half. That's easy. Do we have the ability to get all of them? How? Can we get all of them? This, the same way we got them before. So that's all okay. And if you come in this side,
You can't go that way.
how do you go this way?
Down.
Down.
Up diagonally. Down twice. Down diagonally. Up. Down diagonally.
And out. So if we left out those things in the middle, we can actually get through here, get to everything, come out the other side. What that means is that the pieces of our path now no longer correspond to consistently covering vertices. If we go into B and we cover the edge AB, we don't have to continue and cover BC and BD. We're off in a completely different set of edges. We can cover B and actually get one of the edges somewhere else to get covered too, because we can jump over to where C connects. In other words, it's going to be possible with this kind of component to get a Hamiltonian path in a thing like this, even when there's only one choice here. I'd be able to jump to another component and finish that, even though I haven't finished all the B's. That would mean that if I answered the question here, yes, there's a Hamiltonian path, the answer might be no, there's no vertex cover. And that's bad. So I want to constrain the path so that that can't happen, so that when I do get a Hamiltonian path, I know it corresponds to a real vertex cover. So if I force the component to leave the same side, then I know it has to be covering all the edges that connect to B. Because when it goes in this one and covers the edge BC, it's got to go in this one and cover the edge AB.
Okay, I just need to see the correspondence. I think on this side. Okay.
This big thing here is like one of these things here. So this funny shape here, that's like going through here and making it out the same side.
So if I count the notes, it'll be a count.
Right. Here I'm just making an abstract robot prong with 4 ends, and those 4 ends are the corners here, here, here. So you really do need these silly little things in the middle in order to force you to go out the same side. I think this is the original reduction. Our book has something just like this funny component. I don't know if it's exactly the same number of nodes. They might have gotten it down to 8 or 10 or something. But this was the original one that was published in the first paper that shows Hamiltonian circuits NP-complete. Okay, questions about this? This is Harry. Yeah.
In doing this reduction, it would sort of be horribly polynomial, but it still stays polynomial.
It's polynomial. Yeah.
Some incredibly huge factor to build.
No, how bad is it? It's how bad is it to build this?
12 nodes and a few edges per edge on the graph.
I mean, there's a big constant factor.
Yeah, right.
There's a big constant factor, but I don't think it's more than linear time. I mean, I think you still just do it per edge and per clause. Yeah, certainly there's a big constant factor. Right. Well, look, I mean, would you rather look at vertex cover problems like this or Hamiltonian circuit problems like this? They're the same, really. What I want to do now is back off the reductions for a little bit. They can be very, very taxing and difficult, like I mentioned many times. Let's play a game. Let's play the game. Quickly play this one. Make sure everybody remembers how to play. The 1, 2, 3 game. You want to go first or second. Everybody can pick 1, 2, or 3 sticks on their turn, and the person to get the last stick wins. You want to go first or second? First. So what do you take?
1.
All right. We're not going to bet on this game. I'm going to lose. I pick 2. You guys pick 2. I pick 1. You guys pick 3. And I pick 2. You guys pick 2. And you get the last stick. And here are the key spots. Multiples of 4. We talked about representing every game as a graph. That this game is really represented as a graph, where every node represents a position in the game. In this game, the position is simple. It's just a number. So every node is just a number. It's not like a chess game where every node would be the positions of 32 pieces on the board and exactly where they are. Here it's just a number. And it's a directed graph, 12, 11, 10. 12 goes to 11, 10, and 9, etc., all the way down to 0. Dot, dot, dot. And this game was easy because it had these special winning numbers, the multiples of 4. And those numbers are called the kernel of a graph. What's special about a kernel? Describe to me in terms of graph terminology in English. What makes a kernel a kernel? What do you want to be true about this set of vertices to know that it tells you how to win this game?
3 outs, 1 in.
3 outs, 1 in? I think they all have 3 outs, 1 in, right?
Distance between the kernels.
Because 11 has 2 outs. You know,
11 goes to 10, 9, 8.
Oh, well, I should say 1. Shoot.
I think they're all got the same ins and outs. I don't want you to find the kernel for me. That's what Mike's trying to do, but that's too hard, actually. What I want you to do, in general, finding a kernel is hard. It's an NP-complete problem. What I want you to do is just describe to me what a kernel is. What makes a kernel a kernel?
It can reach our sink in
Right.
exactly
So
2.
the sink actually is the part of the kernel. 0 is a multiple of 4. So number 1, your winning positions better be in the kernel. Okay, so that's 1. Winning nodes all in the kernel. Okay, that's number 1. Number 2, what else? What else makes a kernel a kernel?
Move from one node to another. 2.
It can only,
If you're in the kernel and you make a move, you can't go to another kernel. It's like the frying pan. When you jump out of it, you're in the fire. You're not in the frying pan anymore. So, kernel, just like the bologna tree, yeah. Kernel nodes are never connected. Well, that's not enough. It's not enough just to get a bunch of nodes that are not connected.
every other node connects to it.
Good. That's the second very important thing. If you're in the kernel, you're forced to leave it. When you throw me into 4, 8, 12, no matter what I do, I have to leave that beautiful collection of multiples of 4. And wherever you guys find yourselves outside of the kernel, there's always a way for you to find your way back into the kernel. So, kernel nodes are never connected. Another way of saying every edge out of the kernel goes to a non-kernel. All edges out of a kernel go to a non-kernel, but there is an edge from every non-kernel node to some kernel node. I could have made up this set of properties without making the connection to games at all. I could have said, here's a graph. Here's a few specific nodes that I want in my set. Can you come up with a set that includes all these nodes that are not connected to one another and for which property holds true that all the other nodes outside your set have an edge into your set? Everyone see that's these same 3 things. It's just a graph problem. If I gave it to you like that, it wouldn't make any sense. It's just some retarded definition somebody came up with to do something else on graphs. But it makes a lot of sense in this context. It's this game. If you can find the kernel of a directed graph, you have the secret to that game. You know how to win. You watch somebody play and you can decide. If they're in the kernel, you sit back and put them back in it every time. Back you go, back you go, back you go. Like a good defenseman in hockey. Right in the boards. Doesn't matter where they go, they're in the boards at the end. Ever see a good defenseman? It's amazing. All right. It's New England. We've got to do hockey. On the other hand, wherever your opponent makes their move, you have a move to cut them off. So they're just dead. Now, if a graph doesn't have a kernel, you're stuck. You have no way of just managing it. It's just too complicated. It'd be nice to know if chess had a kernel and what it was. It'd be nice to know if the initial position was in the kernel. The person moves, you put them back in the kernel. They move again, you put them back in the kernel. You write a little program that computes the kernel and checks and puts you back in. You sit back and watch your program play perfect chess. Be nice with any game to know if it had a kernel. So as you might expect, if somebody gives you an arbitrary graph and asks you, does it have a kernel, yes or no, that question is hard. Not even what it is, but just go ahead and answer, does it have one or not? That's NP-complete. Here's a really cool theorem. If you have a graph and there's no cycles, like this game, you notice that this game doesn't have any cycles? You can't add numbers. Every single graph that has no cycles has a kernel. The problem for directed acyclic graphs is completely trivial. If I give you a graph and it has no cycle, and I ask you, does it have a kernel? Here's the program you write. System print line, yes, end. That's it. You say yes. You don't even look at it. The theorem guarantees there's a kernel, and you just say yes. There are some details on how to find it, but you can. There's a polynomial time way to find it. So given a directed acyclic graph, you can find a kernel, you can play a perfect game. So when I describe this game to you, if you think about it in a graph, and if you knew that theorem, you'd know there was a kernel, and you'd know that there's a way to find the game's secret. But the real problem when there are cycles is NP-complete, which is a result you'll see it's tedious and big reduction. It's got some prettier components than what we did today, and it's a little easier to draw. It looks like stars. It'll be a little better. It'll be the last reduction or two that you'll see tomorrow. But what I want to do to finish up today is play some more games.
So if a person could add sticks back in, that would have...
There are all sorts of versions of this. This game is called Variations on NIM, N-I-M. It's about 100 years old, this game, and variations of it. And there's all sorts of cool variations which introduce cycles, which makes the game hard. And there's hundreds of papers published on this stuff. So there's a lot of research here. Chris and Joe. Yeah.
Okay. If checkers didn't have kings, it would be one of these?
If checkers didn't have kings, it would be one of these. Right. You know the game Fox and Geese, where you have four checkers going one way and a king that can go back and forth the other way? And you're trying to blockade the king. There's no jumping. I'll play it with you someday.
I have that at home with Fox and Geese.
Fox and Geese. I don't think that game has cycles. Joe?
Well, chess doesn't have cycles, right?
Sure it does. Because let's say you just moved your knight back and forth. There's lots of cycles. And plus, even worse, you can get queens. The truth is, I should mention, sometimes, even if a graph doesn't have cycles, the game graph is just incredibly huge. So even though you could conceivably say, yes, there's a secret to this game, but practically speaking, even a linear time algorithm to look through it is too long because the actual size of the game graph is too big.
So even if you could figure out what the kernel of chess was,
it's not practical because the number of moves in the game is arbitrarily long, and because we think of the input to that problem as the size of the board, and the number of moves can be exponential in the size of the board. So it's still not a solution, but it's still cool that at least some of these neat games that, like this NIM, you can play. So I want to give you a different version. Maybe some of you have seen this version, and if you haven't, it's just a cool game because there is a secret to it, like this 4-8-12. There is a kernel to this game, but the kernel's not obvious at all. So you can play it for a day before I tell you the secret tomorrow, and we'll play it a little bit now. Has anybody played this game? This is the real version of NIM. Anybody know this game? It's the birthday cake game? No, it's not. It's just sticks. Sticks with a bunch of rows. 3 rows of sticks this time. The game in general has any number of rows of sticks with any number of sticks in each row. But here's one particular start. 3 sticks, 4 sticks, 5 sticks. Same game, except that now you can take as many sticks as you want when it's your turn, but you have to stick to one row. Everybody understand the rules? You can take as many sticks as you want as long as they're all from one row. No, you have to take at least one. You can't pass. Take the last stick. I'll give you a little hint. Has anybody played this before? Does anybody know the secret? So then it won't hurt too much if I give you a big hint to the secret. I'll make my little notes on the side to decide how I'm going to play, because I know the secret to this. Okay, you guys want to go first or second?
First.
Okay, Joe, where do you go?
3.
Take the top 3 off?
Yeah.
I'll just cross them out. I take that one off.
Oh, you can go down below like that, okay.
Take any one you want.
And the trick is to get the last piece off?
Yeah.
3 from the middle row.
Wait, what does the row division mean then? Can you take any?
You can only take sticks from one row at a time.
Okay, so you won.
I won this one. Let's do it again. Joe is right, actually. You do want to go first in this game. What's the right first move? It's not easy. Want to try? Let's play. Be brave. You're not going to be able to win, but you'll be able to discover the secret if you watch what I do here. As long as you don't make it too easy for me. Make me calculate a little bit.
Take 2 off the top row.
2 off the top row. That's the right move. I'll take 1 off here. I'm going to make a star here because this is the right position. Doug went first. He put me in the kernel. That's a kernel position. You're saying, what the hell is that? Fine.
Remove the rest of the middle row.
So Doug's taken this out. That gives me... All right, so I'm going to take 4 off the last one and I win.
Yep.
Except it was my move when you just made a move, right?
Was it?
Yeah, you put me in this position, right?
No, you took 2. You took 2.
Oh, then I took 2 and then he made, okay. So let's put this back where you were. What did I take then? I took 1 off the middle.
Yeah, you got to put the 3 in the middle.
I'm going to put the 3 back. It was like this and I took 1 off. So
Yeah.
1, 1, 1, 1, 0, 1. Okay, this is the position and it's Doug's turn. He wants to turn it into another kernel position.
So if I take 2 off the middle.
2 off the middle.
Yeah.
That's not right.
2 off 4 off the
Oh, wait. 2 off the middle, you said?
Yeah.
2 off the bottom.
4 off the bottom.
3 off the bottom.
Should I give you... I'm going to let you play for a while and think about it. This is a big hint as to how to figure out the kernel. The kernel in this example is nowhere near as obvious as the multiples of 4 idea. But you can represent every position of this game in terms of these zeros and ones that I'm writing here. There's something about these zeros and ones that you can always fix and put back.
Take the 1 off the top.
The 1 off the top.
Yeah.
It's your turn.
Yeah.
So you want to put it into a position that looks like this.
Another.
Oh.
Okay.
Right?
There's.
So I'll take 2 off the middle then. If you take 1 off the top, I take 2 off the middle.
Okay.
I turn it into this. Oh wait, I don't mean that. Ah, I changed my mind. If you take, if this is the position for me, I'm going to make it into this, which means 1 off here. Did you take 2 that time?
Yeah.
Wait.
I take 3 of the
No. Hold on. I'm confused. It was your move. How many did you take at this point, Doug?
1 off the top.
2 of the...
1 off the top.
So there was 3 in the.
Right, and then I turned it into this, which is, so I need to take 2 off here. Yeah, so now it's 3, 3. There's already 1 gone from the top. I'll tell you the secret of this game at the beginning of next class. Then we'll do the reduction for kernel. This is a very nice game, and the secret, it's a perfect game to teach early programs on because it's a nice, you can calculate this in binary and it's really cool. And it isn't obvious. It takes a long time to construct it, but I'll be happy to tell anybody if you play it for a while and give up. I will give you a hint. It has to do with representing these things in binary numbers, and it has to do with something about these ones and zeros. Something that you can always fix, and somebody who's in the bad position always has to mess it up. Whatever they do, they mess it up. Whenever they mess it up, you can fix it. What is it? Think about that, and we'll quit.
And that's on a